All right. So, hello and welcome everyone. Welcome all of you. So, welcome back to this amazing platform Tutee Learning. And today, as we were discussing on the topic of ellipse, so today, following our discussions on the last topic that we have been discussing with the concept of line and an ellipse, right? So, before I proceed to discuss for any other topic regarding the equation of normals following the equation of tangents, I actually want to discuss about one important concept regarding this ellipse, right? So, in an ellipse, when I talk about the line and ellipse, okay, so when I talk about the line and ellipse, so let us consider that a line of equation of the form mx plus c is intersecting mx plus c is basically the equation of the line. So, this is the equation of the line. Now, it meets the ellipse, it meets the ellipse whose standard equation is given as x square upon a square plus y square upon b square is equals to 1. And if I say that this particular line meets the ellipse in two real points, okay, two real points, that means it intersects the ellipse at 2 points. Let us consider the point as capital A and capital B. Okay, now it will intersect at two real points, or it will intersect only at 1 point, or it will not even intersect. That depends upon that quadratic equation that we have discussed in our last class. However, however, in case if this particular thing is a tangent, so in the last class we discussed that if this particular line is a tangent, then the condition of the discriminant should be equal to 0. That basically means there is only one real root, right? And in that case, now how will you obtain this discriminant is very simple. We just put y is equal to mx plus c in this equation and solve for it, right? And we will get a quadratic equation in x. And solving that quadratic equation or the multiple roots of the quadratic equation will actually get me that following condition, right? So if that quadratic equation is having the discriminant to be equal to 0, that basically means it has only one real root, and that is basically the condition of tangency. And in the last class we saw that the condition of tangency is basically given as c square is equals to a square m square plus b square, right? This was the tangency condition that we saw in our last class, right? Now, I actually want to talk about one more thing, is that let us say for an ellipse, let us say this is my x and the y axis as follows. And so for this ellipse, for this given ellipse E, okay, now if I take up 2 points, let us say that any line is passing through 2 points of the ellipse. If I want to take up 2 points and I want to join the 2 points to basically form a chord, right? So here these 2 points will form a chord, right? Now I know that the parametric form of the parametric point or the coordinate of any point on the ellipse can be given in terms of this theta 1 and theta 2, right? So let us say that A point is given as parameter theta 1 and B point is given as parameter theta 2, right? Now if I want to find out the equation of the tangent, or let us say alpha and beta, okay, let us write in terms of standard nomenclature, that is alpha and beta, then I can easily form or write down the equation of the tangent, the equation, oh sorry, not the tangent, it is the equation of the chord, right? So then I can write the equation of the chord here. In this case it is AB. So the equation of the chord AB is actually given by, in this case it is given by x upon a cos alpha plus beta by 2 plus y upon b sine alpha plus beta by 2 a is equals to cosine alpha minus beta by 2, right? So this is how we can also formulate the equation of a chord passing through 2 points whose parametric coordinates are given in terms of alpha and beta respectively, right? So this is the equation of this chord AB, right? So this is a very important and interesting relation that you can also obtain, right? Now in some of the question we'll see this particular form being in application, right? Is this part clear to all of you? Is the discussion clear? Do let me know in the live chat if you have any questions, any queries. We'll try to answer you as much as possible. All right. Okay. So I'm going through a live chat. If you have any queries, any questions, you can let me know. Okay. So following this discussion, let us now proceed for our following discussion on normals, right? So now I think we are ready to discuss about normals. Okay. So as we have been discussing about tangents in the previous class, now if I want to talk about tangents and normal in specific in general, what we actually apply whenever we see any curve. So let us say we have the equation of the curve as some function y is equal to f of x, right? Now, if we want to formulate the tangent or the normal at any particular point, let us say at point P, right? And the coordinate of point P is given as x1, y1. If I want to formulate the tangent at point P, okay, what I actually do is that you can also apply this particular thing, and which we already discussed in our following previous lectures of application of derivative, that the equation of a tangent or the slope of the tangent at any point P can be given by differentiating this particular expression with respect to x at this particular point P, which is basically having the coordinate x1, y1, right? So this is basically going to give me, the slope of the tangent. Okay, this is going to give me the slope of the tangent at point P. And in the similar manner, since the normal to the tangent or the normal at that particular point is just perpendicular to it. So this is my normal and this is my tangent and this is my point P, right? So in order to find out the slope of the normals, which I am writing at m of n, can be easily given as negative times 1 upon the derivative dy by dx at this particular point P, which is having the coordinate x1, y1, right? So from here I can easily ensure or find out my equation of the normal, right? So once I get the slope, I know about the point, I can easily formulate for the equation normal, right? So let us try to do that in the following manner. So if I consider the general equation of the ellipse, so let us consider the general equation of the ellipse of this particular format, that is x square by a square plus y square by b square is equals to 1. That is my standard equation of the ellipse. And if I take up any point x1, y1 and I want to formulate the equation of the normal. Now in this case I want to find out the equation of normal. So first of all I will have to find out the slope, right? So if I want to find out the slope, I will just differentiate it and I will try to find out the dy by dx at this particular point, right? So if I do that from here, at this point P, this will come out to be, this will turn out to be, so if you do that, so let me differentiate it. So let me differentiate both the sides. So if I differentiate both the sides, the first part will be 2x upon a square plus 2y dy by dx, 2y dy by dx divided by b square is equal to 0. So from here, we can obtain dy by dx to be coming out as, so this 2 will get cancelled out because it is common, and I will get the relation as minus of a square upon b square y upon x. Okay, a square upon b square y upon x, right? Now this is at point P, so it will be at x1 and y1, right? So therefore this will give me the slope of the tangent, right? This will give me the slope of the tangent. Now in order to find out the slope of the normal, this will be just inverse of it and with a negative sign. So we'll get the slope of the normal as b square upon a square multiplied with x1 by y1. So this will get me the slope of the normal, right? Now once I have the slope of the normal, I can easily formulate for the equation normal as y minus y1 is equals to slope of the normal, that is b square by a square x1 upon y1 times x minus x1. And if we simplify this particular expression, we'll followingly get our required equation of the normal, that is a square by a square x by x1, a square x by x1 minus b square by y1 into y is equals to a square minus b square, and this can also be given as is equals to a square e square, right? But e is the eccentricity of the ellipse, right? So from here we can easily obtain our equation of the normal, and this is called as the point form. This is called as a point form. Okay, so this is called as a point form of the equation of the normal for our given ellipse. Okay, is this part clear? And similarly, if I can if I just put in place of x1 and y1, so we know that the parametric format of writing down any point on the ellipse is basically given as a times cosine theta comma b times sine theta, right? So if I just substitute here in place of x1 and y1 as a cos theta and b sine theta, we will followingly obtain the parametric form. Okay, we'll obtain the parametric form of equation of normal. We'll obtain the parametric form of equation of normal to this ellipse, and that will turn out to be, so this will turn out to be, so we'll have this as ax secant theta minus by cosecant theta will be equals to a square minus b square, will be equals to a square minus b square, and that will turn out to be a square e square. Okay, so this is how we can also formulate the parametric form of the equation of normal to any given point of an ellipse. Okay, is this clear to all of you? Is this part clear to all of you? Do let me know in the live chat if you have any confusion or any query. Okay, is this part clear? Is this part clear to all of you? Okay, so I am going through your live chats. Let me know if you have any questions, any comments. Okay, and I will try to improve this particular content if you can give me some feedbacks. Okay, so since the JEE mains exam is very near, so this kind of lectures is going to help you a lot, especially if you are revising. Okay, and also we are working on towards providing the one shot lectures, so please stay tuned, and also please subscribe to the channel and hit the bell icon so that whenever we are live you get the direct notification and you can attend the classes live as well, right? So please take the good advantage of this platform so that you can prepare for your upcoming exam in a better manner. Okay, is this part clear to all of you? Do let me know if you have any questions. Okay, so take your time to understand this particular part, because this will actually initially, once getting about the important formula is important, because once you get the formula, the other parts are most of like just practicing it to understand and remember it. Okay, okay, and the only way to remember all these things is just by doing practice and keeping on revising every day. Okay, so since the exam is very near, I would suggest you do keep your revision schedule in such a manner that you are revising almost every day. Okay, at least the 3 subjects almost equally every day. Okay, is this part clear? All right, so let us proceed for the next topic, and that is basically the writing down the equation of the normal in the slope format, right? So previously we have write down the equation of the normal in the point form and the parametric form, but what if I give you the slope of the normal? So that is basically also called as a slope format. Okay, so let us say I give you the slope of the normal and you have to find out the equation of the normal, right? So in this case, if you recall the tangency condition, so from there whatever the tangency condition was given as a square m square plus b square is equals to c square, right? Now this was the tangency condition, right? This was the tangency condition. Okay, this was a condition of tangent. Okay, or I should write as tangent condition. Okay, this was the tangent condition. But now from here, if I want to find out what is the normal condition, what is the condition for normal, which is not different, but we have to actually understand that if that particular line is normal to the given ellipse, then just what we can do is that we can try to solve for the equation of the or the intersection of the point of contact, right? Or maybe without doing all that particular thing also, once we know the normal slope of the normal at that particular point, we can also apply the slope of the normal multiplied with the slope of the tangent is equals to -1 at that point of contact, right? At that point of contact. But if I assume that my line y is equal to mx plus c is the normal to this particular tangent, or is this particular normal to this ellipse, then in order to obtain the normal condition, there are multiple ways to obtain this, right? So the simplest way to obtain this particular condition is basically just finding out. So I will first consider that if this line is a normal to the ellipse, first of all I will consider the point of intersection of this particular line with the ellipse, right? Now once I get the point of intersection of this line with the ellipse, and I will find out that what is the tangent or the slope of the tangent at that particular point. And once I know that, and once I know the point of intersection in this particular term, I will now formulate the slope of the normal by using this particular relation, and following the following transformations you can easily obtain the slope of the normal at that particular point, right? So if you do that, you will followingly get some relation. So I am directly writing the equation over here. So following equation of normal. So if you do the all this algebra and carry it out to get to the equation normal, you will see that the equation of normal will turn out to be of the slope form will turn out to be y is equal to mx minus plus a square minus b square, a square minus b square m square, okay, and whole divided by square root of a square b square m square, right? A square plus b square m square. Okay, so this is the simplest equation of tangent normal in the slope format. Okay, so you can see it is bit different. So previously we were having in the tangency condition the a square m square were together, right? However, in the normal condition the b square m square is together. Okay, and also there is one difference in sign. Here is a minus sign, here is a plus sign, right? But previously it was both plus sign. Okay, so this is the simplest modification. Please take this in mind so that we can apply to following questions, right? Also you can get this following format from here as well, right? Now if you look back over here in this problem over here, in this case the equation of the normal was obtained to be so the equation of normal was if you look over here, the equation normal was basically a square by b square, or from here also we can find out the equation normal, that was basically a secant theta divided by b cosecant theta, right? So from there, so here also we can solve the problem. So having the slope of the normal as, so the slope of the normal from here is basically a secant theta by b cosecant theta, right? So if I simplify this particular relation, it is a by b tan theta, right? A by b tan theta. Okay, so a by b tan theta, right? And I can also equate this to be equation of the normal, right? You can equate this to equation of normal as well, right? And now the conversion that we have to do is that we have to deal with this theta, right? Here the theta point, or it was the parametric point, that was when I compared the x1 y1 to be equivalent to a cos theta comma y sin theta, right? This was the equivalent parametric relation, right? So from there also we can now incorporate for this equation of the normal or the slope of the normal, right? So there are multiple ways to deal with this algebra. I think you can try it out by yourself and maybe we can get to this relation, right? But however, for betterment you can just remember this particular thing for right now, okay? Because when you are going for your examination or this competitive examination, you don't have to actually take all those particular consideration into being. However, if you are really curious into looking into the derivation, I have already given you the hints. Maybe you can try it out to do, and maybe you can arrive at this particular conclusion. Okay, okay. Is this part clear to all of you? Is this part clear? Do let me know in the live chat. Is this part clear or not? Okay. I hope this part is clear. Is this part clear to all of you? So let us now move into discussion about the chord of contact or pair of tangents, right? So let us quickly look into those important miscellaneous topics. So regarding chord of contact, again we have already discussed that when we were discussing about circle, I mentioned that this chord of contact will be repeating in almost all the chapters of conic sections and the formula remains the same, right? So again, for a given ellipse, if I, so let us say this is my standard equation of the ellipse, which is basically E, and from a point outside to the ellipse, if I draw a tangent to the ellipse, so the condition of chord of contact or the chord of contact thing is basically, so if you have this ellipse and if I take up any point outside the ellipse and I try to draw two tangents to the ellipse, right? So from any point outside the ellipse we can draw two tangents, and then if I join the point of contact, so the tangents with this chord, this is the chord of contact. Okay, so this is my chord of contact. Okay, so this is my chord of contact. All right, so I can easily obtain this equation of chord of contact by doing that transformation s is t is equal to 0, right? So the transformation remains the same, that is t is equal to 0, and that can be given as x into x1 by a square plus y into y1 by b square is equals to 1. So this was the transformation for t is equal to 0. Okay, so this is how we can easily obtain the equation of the chord of contact AB. Okay, so this is the equation for the chord of contact AB. Equation of the chord of contact AB. Okay, so this is the equation of the chord of contact AB for the given ellipse. And in the similar manner, we can also obtain the format of pairs of tangents. So pair of tangent equation. So if I want to draw the or write down the equation of the pair of tangents from a point outside the ellipse, that also I can do it by easily doing that transformation that was basically as S1 is equals to t square, right? So this was a transformation that we have learned in our case of ellipse as well, right? In case of circles as well, right? So here in the similar manner, this S will be basically the equation of the ellipse over here, that is x square by a square plus y square by b square minus of 1 multiplied with x1 square by a square plus y1 square by b square minus 1 is equals to t square, right? And t will be basically that point x1 by a square plus y1 by b square minus of 1 and whole square of it Okay, this is how we can easily obtain the equation of the pair of tangent for a given ellipse from a point P which is outside the ellipse, that is x1 comma y1. Okay, is this part clear to all of you? Is this part clear? Is this part clear? Now there are certain more miscellaneous relations that you can also take it up mind, right? Regarding the ellipse is that now in ellipse, the beautiful condition of ellipse is that now if you recall the construction of the ellipse, we have been discussing that if you draw in the construction of an ellipse, we saw that there are two foci, right, or foci or the two focus, right? Now if you recall the distance between of any point, the distance of any point x comma y from the focus, that is pf1 plus pf2 was actually constant, right? The pf1 plus pf2 is basically constant for a given ellipse, and based on this particular condition, we have seen that the ellipse was basically being constructed, right? Now on this regard, there is one more very interesting and fascinating condition is that if you look it carefully, is that if you take up any light source and keep it at focus f1 and you point it such that this ellipse is my mirrored surface, okay, such that this ellipse is my mirrored surface, then this light from point f1 being reflected will always pass through point f2, okay, or this is f2, right? The point from f1 upon reflected, or the light source from f1 upon being reflected at the mirrored surface of this ellipse, whose surface of the equation of the mirror is basically along the surface of the ellipse, then after getting reflected, we will definitely pass through this point F2. Okay, so this is one of the very interesting implication of condition or use of the ellipse, right? So if you go into different engineering applications of ellipse, then ellipse has a very wonderful engineering application, right? Like this. Okay, so when we have to get the, or maybe it can also be not only light source, this can be sound source as well, right? So when we have to trap some enemies, let us say we want to trap some enemies in a building, and we are basically trying to produce some sound from F1, and being reflected it will reach to F2, right? So that is how, or different conditions of reflections can be used over here. But what is important to understand is that light source or any source being reflected or traveling from F1 being reflected at the ellipse surface as a mirror will definitely pass through F2. Okay, so this is one of the very important property regarding ellipse. Okay, so please take that in mind. And also there is one more important miscellaneous question that is also being asked in exams, right? That is, this is kind of a bit of lengthy calculation, but however, if you remember the direct formula, I think it will be easy to basically remember this particular relation, right? So let us say for the given ellipse, if I want to draw two tangents at point A, let us say it is basically alpha, and point B has the parametric coordinate as beta, and if I draw the tangents at point A and B, the tangent will meet at point P, and this point P can also be given as, now please note that this equation of tangent is basically the standard equation, that is x square by a square plus y square by b square is equal to 1, that is the standard equation of the ellipse. So having this condition, then the point of intersection is basically given as, so this is a question actually being asked. So it is basically given as a times cos of alpha plus beta by 2 divided by cos of alpha minus beta by 2, comma, will have the y coordinate as b times sine of alpha plus beta by 2 divided by cosine alpha minus beta by 2. Okay, so this is the point of intersection of tangents drawn at 2 points A and B having the eccentric angles as alpha and beta. Okay, so the point of intersection of tangents at these 2 points A and B is basically given by this following relation. Okay, now this relation is very, very important, especially if you are preparing for your JEE mains examination, because you don't have time to derive this expression, but having this equation in mind or having this formula in mind will actually help you to solve the question quickly and get to your following answer. Okay, is this part clear to all of you? Please do let me know in the live chat, is this part clear? Okay, so let me know if you have any confusion. TV gaming, okay sir, great. TV gaming, uh, I think you are basically attending these classes after a long time, right? You have been not following my live lectures. Okay, so uh, Anshu Kumar, yes, correct, correct. All right, so let us then move towards our discussion on question answer sessions. Okay, so let us take up some few examples from our previous JEE mains paper so that we can understand that whatever we are studying is actually very relevant to whatever being asked in the exam, right? So in that regard, I actually want to give you one problem, especially from your previous JEE mains paper. So this is a very good question, I think. So it is mentioned that there is a point P which is given as 2 root 3 by root 7 comma 6 upon root 7, and point Q and point R and point S be the 4 points. Okay, be the consisting of the 4 points on the ellipse. Okay, be the 4 points on the ellipse whose equation is given as so on the ellipse whose equation is given as 9x square plus 4y square is equal to 36, and let, and it is mentioned, let PQ and RS be mutually perpendicular. So this symbol is basically for perpendicular. Okay, so I'm not writing it completely. Okay, perpendicular and pass through the origin. Okay, and pass through the origin. Okay, now if 1 upon PQ square are perpendicular lines and passes through the origin, and if 1 upon PQ square plus 1 upon RS square is equals to small p upon q, where p and q are co-prime numbers, that is our HCF of this small p and q is equals to 1, then you have to find out what is the value of this small p plus q. Okay, so you have to find out this following expression. Okay, so please give a try. For this given ellipse passing this point P whose coordinate is given, and there is 4 points such that PQ and RS are mutually perpendicular lines passing through the origins. Okay, both of them are passing through the origin. So having been said that, you have to find out the following expression or the following condition. Okay, so please give a try. Please do give a try so that we can discuss about the solution. Okay, sir, be a bit faster, sir. Repeat, sir. Anshu is saying that repeat. This is a question. Okay, TV Gaming is asking what if it is a non-standard ellipse. Okay, if it is a non-standard ellipse, then we cannot apply this equation. Okay, this equation or this formula is only for the standard ellipse. Because so in generally in examination you will only have standard ellipse. Okay, generally. Okay, but if you have a non-standard ellipse, then you have to do it by your own. So it will be more of like more calculations. Okay, so there is no standard formula for it. Okay, so you have to do the calculation on your own. Okay, but for standard case, if the standard case is there in the exam, then you have to apply this formula. Okay. Okay, so please try to solve this problem. Please be a bit faster. Okay, please try to solve this problem. TV Gaming, Anshu Kumar, please try to solve this problem. Alright, so if you look at this problem, so we have to take up 4 points on the ellipse where one of the points is known to us, right? Now how do we solve this problem is a very interesting way. Now if you recall that in our case of an ellipse, when we were discussing about the eccentric angle or how do we take up any point, so generally for any point on the ellipse, so we can take this particular r1 distance, this particular point on ellipse as, so any point on the ellipse can be given as by doing the following consideration, that there is a circle. Okay, there is a circle of this whose diameter is basically along the major axis of the ellipse, right? And we do that, and from there we just project it on the ellipse surface, right? So from there we actually find out the parametric or the form of the point, right? So to consider that laid into being, what I'm basically asking and doing to say that, so instead of taking this r1 as a radius, it is basically taken as square root of a square plus b square, where a and b is at the along the major, semi-major axis and semi-minor axis. Okay, so if I do that, and since point P is known to us, it is basically given as 2 root 3 upon root 7 comma 6 upon root 7, right? This is my point P, right? So if I have this point P and the radial distance of this point P from the origin is given as r1, so I can find out r1 as square root of 2 root 3 by root 7 whole square plus 6 upon root 7 whole square, and that will turn out to be 2 square root of 12 upon 7, 2 square root of 12 upon 7, right? Now if I say that this given point is in terms of polar coordinate, such that this point P is given as, where r1 is a radial distance, r1 cosine of theta comma r1 sine theta. Okay, so if the point P lies on the ellipse, then it must satisfy the ellipse equation. So I must be also satisfying the ellipse equation in this. So if I satisfy this with the ellipse equation, okay, so if I satisfy this in the ellipse equation, which is basically given as x square upon 4 by y square upon 9 is equals to 1, then if I simplify for it, what I will get? I will get some kind of equation of the form that is cosine theta upon 4 plus sine square theta upon 9 will turn out to be 7 upon 49. Sorry, 48, right? 7 upon 48. Okay, so I will get this following expression. Okay, now similarly, if we represent any point r on the ellipse, if we take up any point r on the ellipse, and let us say it is basically given as r2, where r2 is the radial the distance of the point r from the origin as r2 cos theta, or let me take in terms of as r2 sin theta comma r2 cos theta, right? Now why I am doing this kind of modification, you will try to understand this is very simple way, is that I'm just doing a point, I'm taking such a point that is basically having the eccentric angle pi minus theta. Okay, so this is some kind of modification you have to learn with solving some problems. Okay, so this is one of those problems of such example, right? So if I do that, and if I take up, and here the negative sign is being taken in such a manner that it is due to the fact that rs, so this rs chord is perpendicular to this chord which is pq, okay, or this line pq, right? So that's why I'm put a negative over here. And then if I simplify this particular expression, I will get another modified expression as sine square theta upon 4 plus cos square theta upon 9 will turn out to be 1 by r2 whole square, 1 by r2 whole square, right? This is one of the second equation. So let us consider this is my first equation and this is my second equation. So on solving this, my r1 and r2s are basically the radial distance. So this 1 upon pq whole square plus 1 upon rs whole square can be given as 1 by 4 times 1 upon r1 square plus 1 upon r2 whole square, right? And if I substitute the following values, and so also if you note it carefully, that I can also write PQ as 2 times of PO, distance, and my RS as 2 times of OR distance, right? So these are the following distances, and then that's why here I have used 1 upon 4, right? Now also please note that since PQ and RS are perpendicular and pass to the origin, this is valid. And also I need to find out what is my R2, right? So how will I find R2? So we, from equation 1 and equation 2, if I just take this equation, so equation 1 and equation 2, and I just add it, I will get equal to 1, right? So from 1 and 2, so 1 plus 2, I will get the following relation, that is 1 by r2 whole square will turn out to be 1 upon 4 plus 1 upon 9 minus 7 by 48, and this will turn out to be 31 upon 144. So from here I will get this relation of 1 by r2 square, and therefore this will bring me to this particular relation that will turn out to be equal to 13 upon 144. Okay, 13 upon 144 is the final expression or the value of this given ratio of this distance, right? So therefore, and this is as mentioned in the problem, it is basically given as P upon Q. So where P and Q are the coplanar numbers, and therefore I can easily obtain my final result, that is P plus Q, which will turn out to be 157. Okay, I hope this is clear to all of you. Okay, I hope this is clear to all of you. Are you all able to get to this final answer? Sir, I cannot understand. You have to be see, you have to be bit of on the smarter side to understand this particular problem. Is actually what I've done is some kind of bit of modification. Okay, so what I'm actually trying to explain over here is that, so having this ellipse, any point on the ellipse from the origin is actually I'm denoting as r. Okay, so in case of point P from the origin, this is basically given as r, which is a radial distance, right? And I'm assuming this point as r1 times of cosine theta comma r1 times of sine theta, right? And in a similar manner, since this is basically like PQ PQ, and there I also have one more point which is basically RS, right? So there is one more point RS, and since these lines are perpendicular, so if I assume this is basically assumed as theta, so if I assume this is theta 1, then from here this particular line will be nothing but pi by 2 plus of theta 1, right? So therefore this particular angle can also be given as pi minus this entire angle, right? So the modification I am trying to do over here is that I can also assume this particular angles as, so here for point P the eccentric angle is mentioned as theta 1, so point R the eccentric angle is mentioned as pi by 2 plus theta 1, right? Now if we assume for point R, this point R, this value should be equal to R2 times, so this radius is R2, so R2 times of cos of, so instead of theta it should be cos of theta pi by 2 plus theta 1, comma R2 times sine of pi by 2 plus theta 1, right? So having this particular as the coordinates as my point R, so cos of pi by 2 plus theta becomes sine theta 1, and the sine of pi by 2 plus theta becomes cos theta 1, right? So from here we can assume our point R as the follows, right? And also here, since when I do cos of pi by 2 plus theta, it becomes negative. Okay, so please take all this modification into being, and that's why we have mentioned directly over here my point R as minus R2 times sine theta comma R2 times cos theta. Is this part clear? TV gaming, is this part clear? Okay, so these are some kind of interesting modification that you will learn up. Okay, so whenever you are going to give your mains examination, please take this all things into being so that you can easily apply to the questions. Okay, is this clear, TV gaming? Please let me know, yes or no. Is this part clear, TV gaming? See, if you leave the channel, if you leave the live lecture without understanding, then I won't be able to explain you again, right? So you have to take up the explanation when I'm basically explaining you, right? You have to have some patience. Oh, great, TV gaming, that's great. Okay, so please take this thing in being. Okay, so whenever we will solve some other questions of this particular type, please do this kind of modifications. Okay, now generally students basically learn this particular parametric coordinate as a cosine theta comma b sine theta, right? But however, apart from that, we can also represent the parametric form of the any point on the ellipse in terms of the radial distance from the origin, right? Like as shown over here. Okay, alright, so with this we come to the end of today's lecture, and I hope I was able to clear all your doubts, right? So in the next lecture, that's going to be the last lecture on ellipse, we're going to discuss about some of the miscellaneous topics on ellipse, and we're going to solve some previous year JEE mains problems, and along with that we'll also try to solve some JEE advanced problems as well. Okay, so with this I thank you all for your attention, and we hope to see you soon in our next live class. Okay, bye bye, take care, and all the best for your JEE mains.